Hi, welcome to workshop 6 on linear data structures. The topic for this workshop is linked list. The objective of workshop 6 will include to discuss the basic properties of linked list. We'll also talk about the techniques for managing linked list. Other things we'll be talking about will include how to implement an algorithm to handle singly linked lists and other types of linked lists. So we believe that at the completion of this workshop that you should be able to describe the properties of linked lists and other things we have mentioned as the objective of this workshop. It's also important to mention that this workshop is divided into two parts. So we are doing the first part at this moment, and the second part will come up immediately after this first part. Looking at the linear data structure. The linear data structure is a collection of nodes, and that nodes can also be referred to as elements, where each node has a unique predecessor and a unique successor. If you look at this point, you see a node here, for instance, has a unique predecessor and a unique successor. So the only two nodes that are not having unique predecessor and unique successor are the first and the last nodes. Before now, we have been using an array to implement linear data structure. However, there are some problems or challenges or disadvantages of using the array. The thing is that array is static in nature, which means that before you use an array, you have to declare the size of that array. And when you declare the size of the array, imagine when the data you want to use for that array is bigger and you want to extend it. I mean, the size of the data is bigger than what you have declared. So it will be difficult for you to maintain that data structure that you are working on. Extending or reducing the data size is quite difficult. And in order to do that, it's also expensive to maintain. So these are some of the disadvantages of using an array as a linear data structure. So let's also see other things that we've used on the array. We've come to understand that if we want to search for an item in an array and that item is unsorted, then we have to use linear search. So and the efficiency is of the order of n. But if it is sorted items, then we need to use binary search. You remember binary search, we have to divide the list into two and discard the part that doesn't seem to give us the solution. So the efficiency will be of the order of log n. For insertion for the unsorted data, the efficiency is 1. And for the sorted data, the efficiency is of the order of n. Is because you need to move all the data to create a space before you do the insertion for the sorted data. Then if we want to delete any item and that item in the list is unsorted, then the efficiency is going to be 1. The reason is that you wouldn't need to move other data. But if it is sorted, remember it is in a particular order. So you have to move other data in order to make sure that that space that has been deleted will not create a problem, but also for it to maintain the previous order that it has been before. So now this is an activity which is talking about when the position for insertion and deletion is unknown. Remember in the previous one, we knew the positions of where we need to insert the data. So what is the efficiency of algorithm for insertion and deletion of an item into an array that consists of unsorted data? So what do you think will be the efficiency to insert or to delete an item in this kind of an array? You know, in this case, you don't know the position. So for you to insert, you can just, you don't know the position. However, that will not be a factor that will influence your decision because it is unsorted. So you can insert at the end of the array, thereby you don't need to make any shift any other data, and the efficiency will be of the order of 1. Or if you want to delete any item, and even when you don't know the item, so in that case, you need to search for the item, and the kind of search you perform for unsorted data is always linear search. So the efficiency will be of the order of n. So, but for sorted, now will be a little bit different. You know, in the sorted case, for you to insert, you have to check where you need to insert the data because you don't know the data already. And also for you to delete it, you also need to find the location of the data. That will give you a clue of how you can get the efficiencies of these two operations. I'm going back to linked list. The linked list is a collection of objects, and those objects are called nodes. One very important thing to note about this node is that it has 2 components. And one component contains the data, and the other component contains the link. So this is how a node looks like. So this is a node, the whole of this is a node, or you call it an element. The first part or the first component is the data part, and the second part is the link part. So the data part talks about the information, yes, but the link part is the reference part. The reference part is the link part will be linking or referring to another element. So we see examples as we go further, as we progress. And we have already mentioned that the array is static in nature. Comparing it with the linked list is dynamic in nature, which means that we can increase the size of that linked list. Thus, we can grow it or reduce it to fit the size of the data set that we are working on. Now, this is an example of a singly linked list. The singly linked list has a part that is called the head, which is the starting point of the list. Then it has elements attached to them. So all the elements before the last element has a portion for the data and also has a portion that refer to the next node. So this portion is the data that this node contains, and this particular component is the field that refer to the address of this next node. Now, this last one, which is the end of the list, has the link to be null. So any element at the end has the link part or component equal to null. Now let's implement, we are still on linear data structure. Or like we said earlier, so linear data structure has advantages, and one is that it is easily extended or reduced to fit the data set. unlike the array data structure, where the size of the data set is fixed. So the efficiency for insertion is and deletion of data once they are locations are known is of the order of 1. So apart from all this, even when it has all these advantages, also has advantages, it has some disadvantages. The disadvantages, one is that it doesn't allow direct access to the individual data. So in order to access a particular node, you need to find the reference of that node from the previous node. So in that case, if you are performing like a search operation, you have to start from the beginning or the start of the node. Another thing is that it occupies more memory than the array. This is because you need to create another space apart from the data that you need to store. You also need to create another space to store the reference to the next node. Now I'm looking at still on the presentation of singular linked list. So if you want to represent this singular linked list in a Java, so we can declare that the public class node. So the node can be declared as a public. Then you remember that each node has 2 components. So those 2 components are the data and the link. So the data can be a type int, and that type can be any other type. It can be a string or any type of data that you think of. Then this is also another part that is interesting. See, the node here is just a recursive definition of the class node. So we are told to note that the data is an integer here, but it could be any other type of the data. And also the link is referred as a variable. Now, how do we access these components? In order to access these components, we need to understand them very well. So for instance, the first component is the head. And remember that the head doesn't have the data part, it only has the link part. And the link points to the memory or another the address of another node. So first is that the head is a static variable, and that head contains the reference to the first node. This is the first node. So if you want to get the data for this, then we can use head.data. And if you want to get the link, we can also use the head.link. Now, if we progress, we have that this is the reference to the next node, and this is the null, because that is where the link ends. And we also have the data section that stores information about the node. Here is an activity, activity 6.2, which has 2 singly linked lists. And there's a question which says, what is the effect of the following statements on the singly linked list? So if P is equal to T, what is the effect? And again, if P.data is equal to T.data, what will be the effect? Now let's compare the array and the linked list. Remember, we said previously that the array is static, and if we want to access any element in the array, we make use of the index to locate the element to access them. However, in linked list is dynamic, so we can expand or shrink the size of the data. And again, if we want to access any element, we don't use index. We have to look for the reference of that node before we can access it. That's another activity which is trying to measure your ability, how far you've understood what we have been talking about. And that is the treasure hunt. It says that in a treasure hunt, each clue leads you to another clue until you find the treasure. And the question says, how do you know you have reached the end of the treasure hunt? What happens if a clue is removed? The next question is, what happens if you start at the treasure and try to go back to the starting point? The idea here is that we have a treasure hunt, and that treasure hunt, that each clue leads you to another clue, which is trying to say that each node leads you to another node. If you map it with the singly linked list we have been talking about, and wherever you start to move towards finding the treasure, is the head, is equivalent to the head in the linked list. So with this, you'll be able to answer these questions. Now let's look at how we can create a singly linked list. So remember, the first element here is the head, and after that we begin to have other elements. Now, for this head, if you look at the head, you realize that it is you can, if you want to start creating this, you can assign null to a head. It means it doesn't contain any information, because we assume that the list is empty and we want to start creating from an empty list. So the next we want to know is, what do we want to create? Because for any list to be empty or to be null, then that list needs to contain this. So that's how we know that the list is null. So from scratch, we are creating a singly linked list. So assuming we want to start creating from here, in that case, the first element we're going to have will be 6. But before we enter the element, we need to find or create the node. So how do we create a node? We can create a new node by using that new node is equal to P. And what it means is that this new node we have created has no data and it has no link. So we want to insert data. The data we want to insert is 6. So for us to insert the data, then we have to look at this point, which is the node at the moment, the new node. So it's going to be the p.data will be equal to 6. So in that case, we have the data inserted here. And what's the next thing we need to do? So the next thing we need to do is to get the link. However, we can get the link by remembering that before this, that there was a head, and that head will give us the position of the head will tell us the link that we prepare to this place. So, and in our case, we realize that the link that refers to this particular place is null, because it's the first element in the list. So, and how do you get the null value? The null value is already in head. So we have to assign the head to this link. And if we assign the head to this link, then we have that the link will be in this way, or the array, the singly linked list will be in this format. And the last thing we need to do is that we have to put this head to its position, which is here. So if we refer to that, then we have to assign that the P is equal to head, and head will be at this position. So finally, the static variable head has now been assigned and is now referring to the next element. So at this moment, we can say that we've completed this part. Okay, and we have the head referring to this part, this next element. And how about if, so this is what we have. So what if we want to add this one into this place? So the idea is that we want to complete this, form this, create this singly linked list, the whole of this singly linked list. And we started at this point. So the next we want to create is this one. We want to create this node. So in order to create this node, remember, we always use P to create a new node. And once we finish creating a new node, we add the data for that new node. So the data here is 7, and the data could be added to the new node. Now, what is the next thing we need to do? So once we have the data, we need to look for the link. So the link should be pointing to this element here, or the node here. But in the result, what we have at the moment, the link that is pointing to this node is in head. So how do we retrieve the link that is pointing to this node from head? We can do that by saying that the head is now equal to the p.link. So what it means is that we have moved the link. We have moved the link from here to p.link, which is this place. And invariably, this link is now pointing to the address of this node. So the next thing we need to do is that if this link is pointing to the address of this node, then head needs to point to this address of the node, the next node, or the node that will be after the head. So we perform the operation by saying that the P is equal to head. And if P is equal to head, we will now have this operation to be by this. So going through it again, we first had this node, and we had P pointing to it. And that part of P that is pointing to that node is the link part of the P. Now we want to insert a node before the node 6. Let's call this node 6. Then remembering that there was a link pointing to this node 6, and we do not need to mix that link, we have to move that link from where it is, which is at the head, to this position, such that this element will now be pointing to this element. And when that is achieved, we then have to move the link to this element to head, such that we'll now have this at the end. So this is how you continue to create this one, create that one until you complete the task. Let's look at the algorithm. The algorithm for creating a singly linked list. First, we assume that it's an empty list, and if it is an empty list, then the head will be equal to null. So while we need to add more lists, we have to loop and we get the data. We create new nodes which will be referenced to P, and we insert the data into the new node. Then attach new nodes to the front of the list, like we did previously. And lastly, we need to set the head to be equal to P. So for instance, if you have input data XSX, we can create a new node, then get the data to be in p.data, then we get the link to be the head, and we'll now finally assign the head to this. There's an activity which says, why did you choose to create the list backward? Can you create the list forward in forward direction? Let's look at how we can traverse a single list in both directions. So if we were traversing using forward direction, what we need to do is to traverse forward, simply need to look at this condition, that why not at the end of the list, which is when P is not equivalent to null, then there'll be a loop. A loop is simply to process the node followed by the reference, which is via the link component of the node. Then that will end. The other part, which is the backward makes use of the recursive approach. If you look carefully here, you will see walk backwards, and there's a recursive approach of walking backward at this place. So if that's an if statement, that if not at the end of the list, that's when P is not equal to null, then you need to walk backwards to get the link for the head, then process the node data. So these are the processes that are involved in walking backward and going forward for the singly linked list. So now we are moving to inserting a new node into a singly linked list. So there are different conditions to insert a new node into a singly linked list. The first condition is when the list is empty. So if the list is empty, like the one we did in the previous one, where we had only the head, and the head was assigned to null, then we need just to create a new node, and we need not to just to insert a new node only. But if that is not the case, so which means if it is not empty, then we might need to perform further operations. And when it is not empty, it may be that new nodes need to be inserted somewhere within the list. Another condition or another thing is that the new node need to be can be inserted at the front of the list, or the new node can be inserted at the back or the end of the list. So moving forward, let's see an example of these things we've just said. So if you want to insert a new node called Q after node P, so this is the new node that we want to insert, and we want to insert it after node P. How are we going to perform this operation? Remember that if we want to insert it after here, then we need to know the link component of this node, because that link component of this node is very important for this operation. So in that case, the operation that we're going to have, remember this is the Q, is for us to know the reference of this previous one, which is the P. And that previous one will be assigned to the Q, because at that point, this Q will now be pointing towards the next element. And finally, we will assign Q to P link. Another way to do it is to assign Q to P link, then assign the link of P to link of Q. However, these two ways there's one that is the best way or the most accurate way to do it. So which do you think is the most accurate way to perform this operation? So the most accurate way to perform the operation is this on the left. The reason is that you are inserting the element after the P. And because you are inserting the element after the P, you need the reference component of P. And that reference component of P will be assigned to Q. Now let's look at other conditions. So we have a case where we need to insert at the start of the singly linked list. So if we need to insert at the start of the singly linked list, it means that that list is empty already. And if it is empty, the only thing that we have there will be the head. So, and the head we know only has the reference part. It doesn't have the data part. So we need the reference, the head to be assigned to Q, a link, and finally we assign the Q to the head. And if we want to insert the data at the end of the singly linked list, then we have to perform this operation where we need the link of that, element or node and assign that link to the link of the queue. And finally, we assign Q to PQ link. That is how we can perform insertion. Another part that we're looking at is deleting a node from a singly linked list. So deleting a node from a singly linked list could be when we want to delete a node in delete is not, and we found out that that node is not available in the singly linked list. Another condition is when that node is between or within the singly linked list. Another condition is when the node that we want to delete is the first node in the singly linked list. And the last condition is when it is the last node in the singly linked list. Let's now have a look. For instance, we want to delete this node Q. If you look at this, it is not the first condition, but the second condition because it is within the singly linked list. So it is not the first and also not the last. So what do we need to do? We always need to find the pointing, the reference part of that link that we want to delete. Because if we remove this or delete this node here, if we delete this node here, we realize that what we have is this, what we have left is this part of the reference that is pointing to the node that we have deleted, which is not suitable to be linked directly to this node because it will keep pointing to the node that has already been deleted. So what do we do to make sure that once this part is deleted, that this part will then be pointing at the next node? What we can do is to get this part, which is the reference component of the node that we want to delete, and assign it to the reference component of the node that is behind it. So to do that, we have the link of Q assigned to the link of P, and this node will be deleted. So if we continue to look at other conditions, so if the node that we want to delete is the first node, then the link will be the head link assigned to head. Or if it happens to be the last node, then you remember that the last node has null as the value for the link. So the null will be assigned to the p.link. So this is how you can delete a node in a singly linked list. Now let's compare the array and the singly linked list using some of the operations. So for searching an item using the array, in an array, we notice that the unsorted data will be the efficiency of the order of n. But for sorted data where you need to divide the data into two equal parts and discard the part that does not seems to contain the data, the efficiency will be of the order of n. Then for the singly linked list, because the singly linked list has reference of other elements, so which mean each element has the data and a reference to another element. So you cannot divide or use the approach that we use in array list, but you have to go through all the elements before you can get the element that you are looking for. So for insertion, in the case of inserting at the start or inserting anywhere in the list, you need to move the element or create a space for the element to be inserted if we are using array. So in that case, we have the efficiency to be order of n on both cases. But if we want to start at the end where you do not need to adjust any element, then the insertion will be just an efficiency of the order of 1. But for the case of singly linked list, all the operation of insertion is of the order of log n. This is because wherever you want to insert, what you just need is the reference component of the element, and you assign it to the correct element, then you don't need to move every other element in the list. So for deletion is similar to what we had in insertion. The starting, if the element is deleted, if the element to be deleted is at the starting point, then the efficiency will be of the order of n. But if it is at the end, it will be of the order of 1. And if it is anywhere, it will be of the order of n. For the singly linked list, if the item is at the start, at the end, or anywhere, they will all be of the order of 1. And another thing to compare is the memory. Both array and singly linked list have parts that look at the data. However, the singly linked list also has another part that looks at the reference. So because of the addition of the reference part, the memory size or usage for the singly linked list is more when you compare it with the array list. So we'll just come into an end of this first part. And these are the things we encourage or advise that you do. First, you have to look at what we've studied today and ensure that you understand how to implement singly linked list, how to create it, or how to delete or insert an element in it. Also look at the limitations of singly linked list. Check that you understand the difference between the array and linked list, and try as much as you can to attend the exercises. There is also a quiz on the Moodle for you to do. So if you have any questions based on this or what we've thought, you can bring it to the tutorial section, and we will support you on that. Thank you so much, and see you next time.